Hello and welcome back. Let's talk about Stokes' theorem, otherwise known as the curl theorem. Curl, of course, due to this curl of a vector field here. So this might look like a daunting theorem, although it's actually not that complicated. It tells us that we can evaluate a line integral that may be very, very complicated by just representing it as a surface integral where we take the curl of the vector field. These would be the same vector field. Now you might wonder, how can we take a random surface integral from a line integral? Well, this line integral has to be the boundary of some surface S. So here is our surface S in this example, the cylinder, and here is our boundary, or our line, C, that bounds the surface S. So let's use this as an example to prove Stokes' theorem. So first we're going to do it one way, and then we're going to do it the other way. We're going to go from this and evaluate it this way, and then we're going to go from this and evaluate it that way. So the first question is, of course, evaluate the this surface integral where there's a curl under the surface integral. Although that does not make much of a difference because the curl will still give us a vector, where f, our vector field, is a very simple vector field. It is just x, y, and z. And S is the cylinder, x squared plus y squared equals 1. And z spans from 0 to 10, although we will not need to know this since we will not be actually evaluating the surface integral. So let's use this. Well, we know that what we can do is find the boundary of this, and if we remember, z spans from 0 to 10, so at 0, we just have this exact formula. We actually have the curve of a circle, and I forgot to mention in the question that we may assume positive orientation on this circle, and on this, of course, the unit normal vector. So let's evaluate this. Well, we know for a circle, especially a circle radius 1, we're very familiar with this. Our r, we can represent it in terms of theta because that just feels easier. And it's going to be cos theta, sine theta, and we will have to put a 0 here just to specify that this is at z equals 0. Since technically we're in 3D here. So, to evaluate this integral, we will need dr d theta, and then we'll put our d theta at the end of it, as we remember from our line integrals episode. It should be noted now that theta spans from 0 to 2 pi. Since we have a full circle here. Okay, let's get into it. Dr d theta is just equal to negative sine theta cos theta 0. Okay. So let's take our f in terms of theta, and this is just cos theta sine theta 0. It will be exactly like this since we just have this very simple xyz vector field. Okay, so let's dot this with this. What we are going to get is the integral over c of f dot dr is equal to the integral from 0 to 2 pi of negative cos theta sine theta plus sine theta cos theta, I guess we could add plus 0 just to be clear here, d theta. And you'll notice here, this term is the same as this term except one of them is negative, and so this equals 0. Okay, so we know how to do it one way now. Now let's prove Stokes' theorem by performing this the exact opposite way. So we will keep this, and we'll say that this is also our curve. So what we can do is we can create a, first let's draw just like this. This is our 3D coordinate system. And we have our circle kind of coming around like that, if that's well demonstrated. It's on this flat plane right here that's kind of coming out of the board. And so we are going to create a surface that has a boundary around here. This surface is actually just the surface that I created for the reverse problem. Okay, let's figure out what this line integral is now. So, first what we will have to do is find the curl of our vector field. Let's jump right into it. I'm actually going to erase this sketch just so we have a bit more space. The curl of our vector field is equal to the determinant of this matrix. Now, if you see here, when we take this determinant, we will have the partial derivative with respect to y of z, the partial derivative with respect to z of y in our I hat direction. In our j hat direction, we will have the partial derivative of x with respect to z minus the partial derivative of z with respect to, or the partial derivative of x with respect to z. And we will have the partial derivative of y with respect to x minus the partial derivative of x with respect to y. Now, if you were paying attention while I was saying that, you would know that none of these variables match up. And for that reason, this will equal 0, since the partial derivative with respect to some variable that we are performing on another variable, which we therefore treat like a constant, it will be 0. So we have 0 minus 0 minus 0 minus 0 plus 0 minus 0 in the I hat, j hat, and k hat directions respectively. We're always respectful to our variables, but respectively. Okay, so that is Stokes' theorem, otherwise known as the curl theorem. That was our second last video on vector calculus. I hope to see you in the next video where we talk about the divergence theorem. And thanks for watching.